So, I'm Enrico Daniso from the University of Udine, and today I will talk about some methods for the identification of insects in novel food. So, my specialization is not in food, but in detection of different compounds. I work in the University of Udine in the aquaculture department. For that reason, I will start with a general introduction of the use in insects in aquaculture because the European Union authorized the use of 7 different species of insects for aquaculture. And this is quite lovely for us because for aquaculture, it's really clear which species can be used. In contrary, if we change and we take in consideration the use of insects for human consumption, the things change a lot. In the world, more than 2 milliards of people use insects as part of their diet. And edible insects are possible to eat are more than 2,000 species. Why insects are so interested? As you can see from the graph, um, the insects present a high quantity of proteins and fats. For that reason, sorry, for that reason, it's really interested food for in Anglo-Saxon countries, the edible insects are considered as a normal food, not a novel food. For that reason, the commercialization of these foods are not, do not require specific authorization from the government. But for the people that lives in the European Union, the rules are quite different. And especially for the companies that want to sell the product because they produce insects, they should request specific application for the commercialization of insects. And here in this slide, you can see the European Commission portal where the companies should apply and request to EFSA the authorization to commercialize the different insects. At the moment, um, this procedure requests more than 2 years for the approval. For that reason, in European Union, we do not use insects, but there is some exceptions. In these 4 countries that you can see in red, that are Belgium, the Netherlands, Denmark, and Finland, actually different rules are applied for the marketing of insects. And these national rules are different for each country. For that reason, it's really a chaos for the use of insects and commercialization of insects for human consumption. So, novel ingredients as insects, of course, need some specific regulation and uniform regulation for European Union, but especially it's necessary the development of different European system. Sorry, I don't know, my presentation go. We should develop different methods for the detection of insects in the compounds that can be second products or derivatives from insects. Usually, we can use real-time PCR for the detection of these biological metrics, in biological metrics, because it's capable to identify the target DNA of the species in a really complex metrics. And if the quantity of the target DNA is really low, in any case, and this technique is able to identify them. In this slide, you can see the methodology that I think that everyone know, especially in this period, because we know about this corona test and so on. But I don't want to spend so much time on real-time PCR, but I will just bring you some data and that we obtain using some DNA. So when we use the DNA from untreated insect, we can see that we need a lower number of thermal cycle to detect the target. But if the same insect is, in this case, roasted, so get this technological treatment, we need an additional cycle to detect this signal. This is just an introduction because in the following slide, you will realize why I want to underline this. So after the use of a real-time PCR for the detection of insects in complex matrix, we utilize the primers that we identify in the real-time PCR for the to produce a new genosensor for the detection of this species. In this slide, I hope that it's quite clear the procedure that we use to create this genosensor. So we start from the primers that we use in real-time PCR, in this case for the detection of Hermetia inlucens. And we use one primer that is the forward primer, and we attach this primer on the cartridge that is made of polyethylene. And we use the other primer, so the reverse primer, as a capture probe. This primer is actually the complementary primer that we use during the PCR. We made some modification of the primer, and we conjugated this primer with a fluorophore. And in my investigation, I evaluate the different fluorophores that can get a better signal. So as you can see, as you can see, the analysis is composed from the binding probe, the target DNA, and the capture probe. And the analysis in themselves is composed from this cartridge where we bind our probes that I talked before. After this cartridge is put in a oven where we get the reaction between the DNA and the capture probe and the binding probe. So we have a first step at 95 degrees where our DNA is open. And after 1 hour at 60 degrees, where we have the hybridization of DNA with capture probe and binding probe, if the target DNA is present. After we wash our slide and we use this OLED-based fluorescent reader to see if it's present the fluorescence. And this is the data that we obtain, so the image, a raw image, because after we will have artificial intelligence that we analyze the data that we get. But another raw data that we can see is this is the image, but with a high quality, with a different camera, that of course we cannot evaluate the signal with the first two slides, two photos. But if we evaluate the photo in 3D, we can see how in this case, the signal is higher than not in the second case. And actually, this is a correlation with the quantity of available DNA for the reaction. In this case, we use a 25 nanograms of DNA, target DNA in the reaction mix. And in this case, we use just 6.25 nanograms. And the signal is dropping. Because if we compare the data that we obtain from the genosensor and the real-time PCR, we get this scheme. Of course, I should underline that if we, in real-time PCR, if in the real-time PCR we have an increase of the signal when we have less target. In the case of the genosensor, more is the target, higher is the signal. So in this case, it looks like and should be the contrary. And in this image,
and our negative control worth less of this cutoff.
Can you hear me?
Now we
Here, doctor.
The other samples,
but there is some background audio.
Present similar trend for both the systems.
I don't know. Can you hear me?
Yes, there are some noise.
Okay, now better? Okay. So in this slide, we can see how the negative control respect the signal in both cases. And the cutoff is this line. When we go to evaluate the other samples, we can see that with the same amount of target, we have a similar data. But these three samples have the same amount and the same treatment. In contrary, these two samples have the same amount of target DNA, but the treatment is completely different. And as we can see, the amount of DNA available for the analysis is less, or the DNA that we have in the sample is degraded. For that reason, the analysis is not comparable. And this is an important point for me because for each treatment that the food or the feed had can change the results that we can obtain. In all the cases that I examine, in any case, I can discriminate between the positive and the negative, like presence of or absence of the target. But if we want to do a scale and evaluate the quantity in absolute, it's necessary to do further investigation. As you can see from this slide, in any case, in real-time PCR, we have the same problem because if we consider just grillatus, sigillatus in this case, as untreated or in bars or in floor, the data that we get are completely different and they can respect the same trend if we consider just the same treatment. But if we compare the different treatments, we get really different results. So in conclusion, I would like to say that real-time PCR, as we know already, it's a really good method for the detection of targets and contaminants or different DNA that we want to find in feed or food for frauds or to evaluate the quality of the raw materials. Of course, the pair of primers that we choose is always important to define a really good real-time PCR. In this case, with the primers that we obtained, we were allowed to create this new DNA biosensor that was capable to provide us similar results that we had in the real-time PCR, but further investigation must be done to certify this trend. In any case, we should always evaluate that technological treatment had a really big influence in the quality or availability of the DNA for our analysis. So thanks for your attention, and I hope that I will just transmit you my focus and a little bit of my research. Thanks for your attention.